Hi, my name is Adithi Wijesekera, and my Khan Academy video was from problem set 6, question 5, parts A, B, and C. This is the Aqueous Ionic equilibrium chapter, and this problem is focusing on titrating a weak base with a strong acid. The question states you conduct a titration of 25.0 milliliters of 0.175 molar ammonia by adding 0.150 molar hydroiodic acid. So in this problem, we're given the volume of the analyte, the ammonia, which is 25.0 milliliters, the concentrations of ammonia, which is 0.175 molar, so that's in moles over liter, and the concentration of the titrant hydroiodic acid, which is 0.150 molar, which is once again in moles over liter. So I'm going to analyze each step A, B, and C as we go. So step A is just asking us to write out the chemical reaction that represents the titration. And so for that, the approach we take is just adding together our two reactants, ammonia and hydroiodic acid. And the products we get are ammonium and the iodide ion. Now for part B, it's asking us what the initial pH is before any acid is added. To preface, we know that if there's just base in the flask, that the pH should be basic and greater than 7. And basically what we're going to do is set up a rice table to help us eventually find the pH of the sample. And so the equations we're going to use is that Kb, the base dissociation constant, is equal to the concentration of the products over concentration of reactants. POH is equal to negative log of the concentration of OH minus, and that the pH plus the POH yields 14.000. And so first we set up our rice table. In the first row, we write our reaction. NH3 plus H2O is in equilibrium with NH4 plus OH minus. In the next row, we write down our initial concentration, 0.175 for NH3, nothing for H2O, and 0 for the two products. Minus X and plus X are the concentration changes for the reactants and then the products, and then what our equation is going to look like with the 0.175 minus X and then the X's for the products. And so now we can set Kb of NH3, which we find to be 1.76 times 10 to the negative 5, equal to the concentration of products, X squared, over concentration of reactants, 0.175 minus X. For this problem, we're going to assume that X is small, which allows us to cancel out the X that's in the denominator. So we have 1.76 times 10 to the negative 5 equal X squared divided by 0.175. We multiply both sides by 0.175 to remove the denominator, and then take the square root of X to isolate X. We find that X is equal to 1.75 times 10 to the negative 3 molar, which is equal to the concentration of OH minus. To find the POH, we take the negative log of OH minus, and we find that it is 2.757. We subtract this from 14 to find the pH, and we find it to be 11.243, which is basic, and it makes sense because no acid is yet added. Now, for part C, it's asking us what the pH would be after we add 5.0 milliliters of hydroiodic acid. As a general concept, we know that the pH we end up with here is going to be less basic than our original pH from part B because we are adding an acid. So the pH of this component should be less than in part B. In this problem, our approach is going to be to find the number of moles left of the substances so that we can calculate new concentrations of the base and acid, and then use Henderson-Hasselbalch equation to find the new pH. The equations we are using are pH equals pKa plus log of the concentration of base over acid, which is Henderson-Hasselbalch. Molarity is equal to moles over liter, and Kw is equal to the acid dissociation constant times the base dissociation constant, which equals 1.00 times 10 to the negative 14. And so first we write our equation, NH3 plus H plus yields NH4 plus. We now find the number of moles of both NH3 and H plus, and we use the number of liters of both components and multiply that by their respective molarities. And we find that the number of moles of NH3 is 0.00438 and number of moles of H plus is 0.00075. And we find the number of moles of NH3 left by subtracting that H plus moles from the NH3, and we find it to be 0.003625 moles. Now we need to find the new concentrations. Our new volume is equal to 0.0250 liters plus the 0.0050 liters of acid added, which is 0.0300 liters. And so to find the concentrations, we use the moles that we found above and divide by our new volume, and we find that the new concentration of NH3 is 0.12 molar, and for NH4 plus, it's 0.025 molar. And now we can use Henderson-Hasselbalch. But first, we need to find what Ka is equal to, because previously we were using Kb from NH3. We do 1.00 times 10 to the negative 14 divided by the Kb value, and we find that Ka is equal to 5.68 times 10 to the negative 10. And now we can plug in this Ka value and the concentrations, the new ones, of the base and acid, and we find that the pH of this solution is now 9.93, which is less basic in the original, and this makes sense because acid was added. And so those are the three parts of the video. This was a problem where we titrated a weak base with a strong acid. In part A, we were asked about the chemical reaction that occurs during the titration, and we received our answer by considering the reactants and products. Our answer was NH3 plus HI yields NH4 plus I minus. For part B, we were asked about the initial pH before acid was added, and we used a Rice table to find X, which was the concentration of OH minus. From there, we were able to calculate the pH of the solution and saw that the answer was 11.243, which makes sense because no acid was added yet. In C, we had to find what the pH of the solution was after adding 5.0 milliliters of acid to the ammonia. The method we used was finding the number of moles of the substances, calculating new molarities, and then using Henderson-Hasselbalch to find the new pH. We've received an answer of 9.93, which makes sense because adding a strong acid decreased the pH. Thank you.